Okay, so the purpose of this video is to go over how we used statics to solve this problem. And statics is the study of systems which are not in motion, hence the name statics or static equilibrium. It is extremely important because a lot of things, mainly structures, are not supposed to be moving. So it is important for engineers to learn how systems behave with forces applied to them. So this particular statics problem, we use MATLAB to solve it. And this is the problem. This is the picture. Consider two cables connected at anchor points A and C and held in static equilibrium by a cable with tension AB and tension AC. The distance between the two anchor points is d in feet. The cables hold a block with the weight W. The image below is a depiction of the system. So that's that. Now let's go up here. And this is a redrawing of it. And I changed a couple things. I renamed point B A and C stays the same and point A B. And everything else is still the same. This is still length D. So the next step now is to draw a free body diagram of the system, which will dumb it down and help us solve it. And there are three vectors. There's the tension in AC, the tension in AB, and the weight W. And it has angles theta and phi. As you can see that this only has a negative y component. These two have positive y components. This one has a positive x component, and this has a negative x component. This is important for when we make the equations to solve it, which are over here. So in statics, you pretty much use two equations, which are the sum of the forces need to equal 0, and the sum of the moments need to equal 0. Thank God that we did not need to use the sum of the moments. So the first step is the sum of the forces in the x direction equal to 0. So we have the tension in AB cosine theta plus the tension in AC cosine phi equals 0. The reason this is negative is because this has a negative x component. So these two need to cancel each other out and equal 0 so that there is no horizontal movement. Then the sum of the forces in the y equal to 0. And we have negative W plus the tension in AB sine of theta plus the tension in AC sine of phi equals 0. And we use some algebra to simplify it. The third step is to solve for TAB, and that's how we do that. The fourth step is to plug TAB into the sum of the forces in the y equation. And we do that here. We plug this in right here. And using some algebra, we turn this into this, a little cleaner. In step 5, we factor out the tension in AC, because as you can see there was tension in AC here and tension in AC here, so we can pull that out. And then we divide it to the other side, so we have W over all this, and that's why I called it blah blah blah. Now we have the tension in AC is equal to W tangent of theta, W over the tangent of theta cosine of theta plus the sine of theta. We use MATLAB to solve for this, and then in step 6 we use the solution of this to go back to our original equation and solve for that. And that's how we get the tension in AB. So that is how we're algebraically going to solve for it. Now in MATLAB, this is our algorithm. First step is to find the min and max length of AC. 2, create a row vector. 3, solve for the angles using the law of cosines. And then 4, solve for the tensions. So let's move over to MATLAB. Oops, this is still running. Alright, so here we have our normal housekeeping commands. This is used for a loop, which I'll get to later. And then here we are importing our data from an Excel spreadsheet. And here we have data validation. This is a for loop to move through all the data. And these are conditionals. Here we're checking that everything is positive. If not, we use absolute value to make it positive. Then here we are checking that the length of AB is less than the length of D. Here we are, if there is an error, in other words that the length of AB is greater than the length of D, then we have user input to change that. Here's again the while loop. That was where the again came from, up here. Then we have user input asking them which row they would like to test. And this is for the Excel spreadsheet because it has several rows of data and the user needs to choose one. Otherwise there'd be a million plots popping up and that would be no good. So here we're making sure that the user input, they actually input a number which is a row, like not a negative number or something. Here rename the data into DW and LAB just to make it easier to read. Then we determine the max and min of cable AC, which is the first part in the algorithm. So the minimum length of AC would be D minus LAB. The max length of LAC would be the square root of LAB squared plus D squared. And this is because, back at this picture, when this is at 90 degrees, this would be at its longest point. Because if this was an obtuse angle, then this cable would have slack in it, and then it would be doing nothing. Or it would have no tension. So here we have the function file which is being called, which is over here. There's a for loop that runs through the min to the max, and then it solves for the angles here. It solves for theta and, the tension in AC and tension in AB using the equations we came up with earlier. Here we have the plotting. Here we're finding the min and max of the tensions. Here here's the minimum, here's the maximum. Here we find the intersect of the tension AB and tension AC to find where they have the exact same tension. And here we have the formatted output and a menu to ask if we would like to run it again. So let's run this. Alright, so here we have some errors where the length of AB is longer than the length of D, so let's fix that. There's another error. So now it's asking me which row I'd like to test. So I'm just going to pick a random number, let's say 5. And here we have the graph. So as the length in cable AC increases, this is how the tensions look. And that's how that works. So there are some issues with this code, or limitations. One, sometimes there is no intersect, as you saw in that graph, that they didn't really touch. And that's really about it.